So most of this course has been about identifying efficient solutions to problems. But it's also important to realize that there are some situations where no known efficient solution exists. And we have to be able to recognize this so that we don't fruitlessly try to look for solutions where the problem is known to be hard to solve. So let's look at some issues involving intractability. So in many of the problems that we have seen, we are trying to search through a number of possibilities to arrive at some kind of optimum combination. The actual search space is exponential. If you are looking for shortest paths, there are an exponential number of paths. If you are looking for a minimum cost spanning tree, there are an exponential number of such spanning trees to search through. If you are looking for the maximum flow, we have many different ways of adding and subtracting flow along edges. So if we look at all possible flows, all possible paths, all possible spanning trees, and then choose the optimum, this would be a brute force solution which would take exponential time. When we have a polynomial time algorithm, we are actually cutting through this exponential and in some very drastic way reducing our search space from an exponential one to a polynomial one. So it is tempting to believe that if one just thinks long enough and hard enough, that any such problem we will always find such an efficient shortcut, okay, where we can cut through the exponential space of possibilities and quickly narrow down the space to a polynomial number of realistic ones from which the efficient solution, the actual solution we want, will emerge. Now, unfortunately, this ideal world is not actually the way the world is, right? So there are many problems for which efficient algorithms don't exist or are not known to exist. And unfortunately, also many of these problems are extremely important practical problems. So to get into this discussion, let's talk about the difference between generating a solution and checking a solution. So supposing a school maths teacher assigns the following homework. Okay? Take a large number which is known to be the product of two prime numbers and find these two prime numbers. Okay? From the student's point of view, obviously, the problem is to generate the solution. So given the large number n, the student is expected to find two prime numbers p and q such that p times q is equal to n. Now the students submit their solutions to the teacher for evaluation. So the teacher is in a much better perspective, right? The teacher doesn't have to keep generating p and q. The teacher doesn't even need to know the answer, right? So the teacher can just take the answer given by the student, multiply p times q, and determine whether p times q is equal to n or not. So even without knowing the answer, or even if the answer is wrong, the teacher may not know the right answer, the teacher can decide whether or not the student has given the correct answer. So what the teacher is doing is checking the solution. What the student was trying to do was generate a solution. So this gives us a notion of a checking algorithm, right? So if I have a problem, I can say that I have a checking algorithm if for every instance, okay, I can take a solution to that instance and quickly verify whether or not that solution is actually a valid one, right? So a checking algorithm takes an input for the problem, a solution which is maybe not just the solution but solution plus some extra information, right? And then it determines whether or not this is a valid solution. If so, it says that the solution is correct and outputs yes. Otherwise, it says no. So in our example before, the factorization example, the input instance is the number n to be factorized. The solution that we get as a candidate to solve the problem is the pair of primes p and q that the student has calculated. And the checking algorithm involves verifying that p times q is actually n. So in this context, let's look at a very canonical problem which has a checking algorithm called Boolean satisfiability. So we have some Boolean variables x, y and z. So Boolean variables can take values true or false. And we have the standard operations on Boolean variables. Negation takes a value of true and turns it into false and vice versa. So we write that with this exclamation mark using some programming language terminology. So not x is written as exclamation mark x. Then we have x or y, which is true provided at least one of them is true. So if either x is true or y is true or both are true, x or y is true, we write that with this vertical bar or pair of vertical bars. And we use ampersand to denote and. X and y is true only if both are true. So x must be true and y must be true. If either one of is false, x and y is false. So this is the standard Boolean operations that we know about Boolean variables. Now we set up Boolean formulas in a very special form. We first construct what we call our clauses. So a clause is a big disjunction. It's X or y, not Y or Z or something. So what is inside the disjunction are either variables or their negations. So these are called literals, right? So a literal is either a variable or a negated variable. So clause is read as this clause is X or not Y or Z dot 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 or W. So this is a clause. And then finally a formula will be a combination of such clauses connected by ands. So C will be some X or Y or something. D will be some Z or not Y or something, and so on. So each clause will have the structure of a big disjunction of literals, and then they are combined by an ampersand. So they are all ANDed together. So I need to make clause C true, and I need to make clause D true, and I need to make clause E true, and so on. So our goal is to find out whether this given formula can be made true by assigning suitable values to X, Y, and Z. Okay, all the variables in the formula. So this is called a valuation. So a valuation is a function that says X is true, Y is false, Z is true, and so on. So it fixes the value of each Boolean variable. Now having fixed that, I can evaluate, right? So for example, if I take X to be true, Y to be true, and Z to be false, okay, then here for instance, in this clause, X is true, so that's enough to make the whole clause true, Y is also true. In this clause, for instance, X is true, so this part is true, X is true. Here it says Y is true, Z is false, so both of these are actually true. And now here it says X is false, okay, not X, but X is true, so not X is false. Y is true by our valuation, not Y is false. But fortunately Z is false, so not Z is true, right? So in each of these clauses, at least one of the literals becomes true under this valuation, so this entire formula is actually satisfiable. Now, if I add this extra clause here to the same formula, now it turns out there is no way to find any way of assigning true, false to X, Y, Z to make it true. You can check that this particular valuation doesn't work because if I look at this, it says that X is true, so this doesn't work. And it says that Z is false, so this doesn't work. So Z is false, so Z is not true. Not X is true, so not X is false. So this is false or false. So this clause actually evaluates to false. So this particular valuation which made the first formula true doesn't make the second formula true. And in particular, no valuation will actually make it true. And that can actually be checked if you look at these three clauses. Okay, this can be said as that Y implies X. What this says is that if Y is true, then X must be true. And this says that if Z is true, then Y must be true. And this says that if X is true, then Z must be true. So this more or less says that X, Y, and Z must all be the same. But then if X, Y, and Z is all the same, then either one of the first or the last clause is going to be false. Actually, there is no satisfying assignment. So our goal is to find out whether there is a satisfying assignment or not. Right? So to generate a solution, of course, the brute force approach is to try assigning each of X, Y, and Z true and false in turn. And then once we have assigned X, Y, Z to be true, false, we can evaluate it and check if the formula is true. And we try this for every possible such assignment. Okay, there are n variables. Each of them has two possibilities. Clearly, there are 2 to the n. Okay, so an exponential number of possible assignments. Now, the amazing thing is that in general, no better algorithm is known for this problem. Okay, at the moment, as things stand, we do not know an efficient way to take a formula in this form and find out whether it has a satisfying assignment. However, it's easy to check that it has an algorithm which can check a solution, right? So if I give you a formula and I claim that a given valuation is actually a satisfying assignment, all I have to do is plug in that assignment, like we did for the earlier case. I can say, oh, you say Vx is true, let me put true everywhere I see X. You say Vy is false, let me put false everywhere I see Y. And then evaluate the formula, find out whether the ands and the ors add up to a true answer or not. So it's easy to see that this has a checking algorithm, but it doesn't have a generating algorithm. At least we don't know of one. So in this case at least, and in other cases also, sometimes the presentation of the problem is important. So we said that a clause was a disjunction of literals and then a formula was a conjunction of clauses. What if we reverse this? What if we say a clause is a conjunction of literals? So in the clause, I connect everything with and then I connect the clauses with or. This means that I must make C true or D true or E true. Earlier I had to make C true and D true and E true. Now if I look inside a clause, how do I make a conjunction like this true? Well, it's easy, right? I must make each of these true. Unless I make everything true, this whole and will fail. So if I take a clause, then the settings of the variables inside the clause force me. It says x must be true, y must be, not y must be true, so y must be false, z must be true, and so on. So I don't have much choice. Now inside a clause, I might see not y, and then somewhere else I may see y. Right? So therefore, this such a thing will say, oh, I'm being asked to set y true and y false, so this clause cannot be true. Then I move to the next. So I look at each clause, I check whether the unique valuation it insists on is plausible or feasible. If it is, I'm done, because I only need to satisfy one clause. Otherwise, I move to the next one. Right? So in a linear scan from left to right, I can basically solve this problem if it is given to me in this form. Okay? Whereas in the earlier form, there is no efficient algorithm. So clearly the presentation of the problem is important. So let's look at a completely different problem. So we have this well-known traveling salesman problem. So a salesman is supposed to visit a network of cities, and between each pair of cities, we have a distance. Right? So we can think of it as a complete graph. Every city is connected to every other city, and on each edge between two cities, there is a weight indicating the distance or the cost or the time or some quantity which the salesman has to use up in order to travel from the one city to the next city. So the salesman's goal is to visit every city on this map. Right? So the salesman wants to find the shortest tour that visits each city exactly once. So in a graph theoretic sense, what it means is that you have a simple cycle. Simple cycle means that no nodes repeat. I don't visit the same vertex twice along this thing, which starts and ends at the same state. That's why it's a cycle. So we start and end at the same city, same vertex, visit every vertex in between, and of minimum cost. So once again, there is no simple way to write a generative algorithm which will actually analyze this and find a good solution. Okay? So now our question is there a checking solution? Is there a checking algorithm? So recall that what a checking algorithm does is it takes as input, it takes an input instance and it takes a solution and then it says yes or no. Okay, this solution works, this solution doesn't work. So now we have a graph and somebody gives us a cycle. Okay? We can verify that's a cycle. So that part is easy. We can even compute the cost of the cycle. That's also easy. But how do we know that among all the different cycles, this is the least cost? Right? So it's not very clear that there is a checking algorithm because in the end, though we can verify part of the solution, that it is a cycle that visits all the cities and we know its cost, we have no way without solving the problem. Remember, the goal of a checking algorithm is not to solve the problem. It's to ask whether this given solution is correct for this given instance. So we may not know how to solve the problem. Like the teacher who's assigning the factorization homework. The teacher does not need to know how to factorize, does not even need to know the factors. The teacher only needs to know how to multiply two potential factors and check whether the answer is the same as the big number given. Similarly here, we just need to check whether the given nodes form a cycle, but unless we know how to solve the problem, the checking algorithm cannot figure out whether it's a least cost cycle or not. So how do we get around this? So the solution in such optimization problems to convert them into checking algorithms is to transform the problem by giving a bound. Okay, so you give an upper bound or a lower bound depending on how. So in this case, we will not just ask if there is a tour, if there is a traveling salesman tour of lowest cost. We will say, is there a tour with cost at most k? Okay, so we have just given a bound on the cost. We are not asking for an optimum tour. We are only asking for a tour which does not cost more than k. Now we are given a solution, we can check it because we can check its cycle and then we can add up all the edges which form part of the tour and find out whether it adds up to k or less. Right? So how does this help us? Okay, because our goal was to find the shortest tour. What we have said now is that if I give you an upper bound in the size of the tour, I can use a checking algorithm for yes or no. But now we can try a different case, right? So we have the minimum value of k is clearly 0, okay? And the maximum value is some upper bound. What is a good upper bound? Well, we know that a tour is going to take edges from the graph. If I take all the edges in the graph and add up all the costs, the total tour cannot be more than that. Okay. So I have a range of values possible for the cost of the tour from 0 to say the sum of all the edge weights in the graph. You might even find a better bound than that, because obviously you can't use all the edge weights. You can only use n of them to complete a cycle of size n. Okay, but this is a very conservative bound. Now what we do is, we do in this range we do binary search. So we first check, is there a tour of whose cost is midway? If there is, then I will now check below, is there a tour of cost half of that? So by doing a binary search, we narrow down the thing, and finally we'll find that this is the level where we have a tour, and above that we have tours, and below that we don't have tours. So this is the minimum cost tour. Okay, so by using a binary search and an upper bound, we can take an optimization problem where we are looking for an optimal answer and transform it into a sequence of checking problems, which after a logarithmic search through the space of the bounds will give me the actual solution I want. So here is yet another problem. So this is called the independent set problem. So we say that two vertices are independent if they are not connected by an edge. So for example, here if you look at say 1 and 7, then they are independent because there is no connection. Similarly 6 and 5 are independent. Okay. So we say that two vertices are independent if there is an edge. Now if I take this set, if I take 1 and 7, this is independent. But if I add 5 to it, for instance, now 5 and 7 are connected by an edge, so these are not independent. So an independent set is one in which every pair is independent. Okay, so 1 and 7 is an independent set, but 1, 5, 7 is not an independent set because 5, 7 is an edge. So here for instance, you can check that 3, 4, 5 forms an independent set. Okay, because there is no edge between 3 and 4, there is no edge between 4 and 5, there is no edge between 3 and 5. So for example, if you are trying to, if you say you interpret these nodes as people and you note edges as knowing each other. So supposing you want to set up some kind of a committee where you want to be sure that all the committee members have independent opinions and are not influenced by the facts that they know each other before that. Okay? Then you can pick up an independent set. So an independent set will produce people who mutually do not know each other. So therefore, when they meet for the first time, hopefully they have neutral opinions about each other, about the problem that they have. Okay, so this might be one example of why you want to pick up an independent set. So the algorithmic problem is to find the largest independent set, right? So here we have found an independent set of size 3. Can I do better? Can I find one of size 4? Maybe, maybe not. Right? So this is my algorithmic problem. Given a graph, what is the largest independent set that I can find in it? Now, as we saw before, this is a problem where we have to get an answer. So if somebody tells me 3, 4, 5 is a maximum independent set, I can verify easily that 3, 4, 5 is an independent set, but I cannot necessarily verify that there is no larger set. Okay, this is like the traveling salesman problem where I can verify that the tour given to me is a simple cycle, but I may not be able to verify that the cost of this tour is the best among all such tours. So once again, if we want to set up a checking version of the problem, we will set a bound. We will say, is there an independent set of size k? Okay, so we are trying to find the largest one. Okay, so we will say at least size k. So if I say at least size 3 and this produces this, I will verify it as size 3. If I have said at least size 4 and this is my witness, this is my solution, I will say no. Right? So independent set, again, like traveling salesman and Boolean satisfiability, we don't know of a good generative solution. Okay? But by using this bounded version where we provide a number for the quantity we are trying to estimate, we can produce a checking version. So a related problem to this is called vertex cover. We say that a node U covers every edge that is incident on it. So for example, if I take this node, then it covers these 4 edges because all these edges start at 2. Okay? So now a vertex cover is something that covers all the edges. So for instance, if I take 2, I cover those edges. Now this edge is not there, so maybe I take 3 to cover it. So I take 3 and this covers these edges. Now I still have some missing edges, so maybe I pick up 7. Okay, so 7 covers these 3 edges. Okay. So now I have found a collection of 1, 2, 3 vertices which cover all the edges in this graph. Okay. So now what we want to do is find the smallest vertex cover in a given graph. Right? And again, because we don't know how to do smallest in general, okay, we will say that we will take any vertex cover which is at most size k. Okay, because we're looking for the smallest one. So it is like the traveling salesman, we're looking for the shortest tour. So we'll say, is there a tour of less than or equal to certain cost? So is there a vertex cover less than or equal to certain size? So these two problems look connected, and in fact they are. Okay. So here, for example, we have a vertex cover of size 4, which is indicated in green. So the connection is that U is an independent set of size k, if and only if its complement is a vertex cover of size n minus k. Right? So in our case, U 3, 4, 5 was a vertex independent set of size 3, then its complement must be a vertex cover of size n minus k. So if I could solve the vertex cover problem for a certain size, I can solve the independent set problem for n minus k. So I can convert one to the other. Okay? And the proof of this is very easy. Okay? So supposing I know that U is an independent set. U is an independent set, then no edge is within U. Right? So if I take any edge, UV, okay, then if one end is inside U, the other end must be outside U. Right? Or both endpoints are outside U. So therefore, if I take any edge, at least one of its endpoints lies in V minus U. So V minus U covers all the edges. So therefore, V minus U is a vertex cover. And of course, given that this has k vertices, the other one must have n minus k vertices. Conversely, supposing I assume that V minus U is a vertex cover, then every edge starts from there. Okay? If every edge starts from there, one of its endpoints is there. So I cannot have an edge which is entirely within the complement, because if I have an edge which is like this, then this is an edge which is not covered by the vertex cover. Right? So there cannot be any edges within U, therefore U is an independent set. And once again, the sizes are guaranteed because they are complementary sets of vertices. Right? So this says that independent set reduces to vertex cover with the complementary size. This is the bounded vertex version. And vertex cover reduces to independent set. Right? So they reduce to each other. So when we introduce reducibility in the context of linear programming and network flows, we said that one aim is to transfer efficient solutions from B to A. So when I reduce A to B, if B is efficient, then A is efficient. But in this context, what we are trying to say is that if this is not known to be efficient, then this also is not known to be efficient. Right? So since independently, we believe that independent set is not efficient, then because it reduces the vertex cover is also likely to be not efficient, and vice versa. Right? So it turns out that many pairs of checkable problems are such interreducible problems, either directly or we might find a cycle of things. A reduces to B reduces to C, and C reduces back to A. Right? So in that sense, all of them are equally easy or equally hard, and since we tend to believe that nobody has solved any of them yet, that they must all be hard, okay, this gives rise to the belief that there is a large group of problems which are actually practical in terms of their usefulness, but not known to be efficiently solvable in terms of our notions of algorithmic efficiency. So we will look at this a little more detail in our last lecture.